Now that we have an understanding about thermodynamics, and we've learned that the enzyme lowers the activation energy by binding the transition state best, let's start talking about some models that describe the kinetics more quantitatively. And I should say from the outset that these this is really relevant to what you'll be doing in the biochemistry lab when you will be assaying the activity of lactate dehydrogenase, LDH, your frenemy, in the presence of and absence of inhibitors, and you'll be interpreting the data. It also is quite apt for those of you who are in physical chemistry or who have been in physical chemistry, in which you'll be getting into a more quantitative description of kinetics, okay? Just like you'll be getting into a more quantitative description of the thermodynamics in physical chemistry as well. So I think many of you are appreciating the interconnectedness of the coursework that you've taken during your time at UMD in your majors, but you'll continue to see this connectedness as we move forward. And, as you move forward in your training and education and career. So always be aware of these different connections. You guys are just amazing. So off my little soapbox, let's get on to kinetics and mathematically describing them. And so why in the heck would you even care about studying kinetics? Like, who cares? Well, it informs us about the mechanism of action, okay? And we can begin to determine how the enzyme's activity may be regulated, okay? The substrate, the enzyme itself, we can also, if there are non-natural substrates, i.e. a drug of some kind, this will also affect the enzyme activity, but we won't be able to assess that unless we can analyze the kinetics of that enzyme. And of course, temperature also plays a role, because it is that factor T in all the equations that we've been seeing, okay? Although physiologically, temperature doesn't vary unless you are like a bacterium. But for us mammals, it's pretty steady, even when it's minus 35 in Minnesota. Okie doke. So we can write out, as we've seen before, our enzyme, our substrate, forming the Michaelis complex with certain kinetics, and that complex can dissociate back into substrate with certain rate constant. Or alternately, the substrate can move forward into product. And we'll talk more about this particular reaction momentarily, okay? But I just wanted to give you an example of how one might write out a reaction describing the kinetics. This is not the only one. There are many ways. Of course, it depends upon your specific enzyme of interest and substrate of interest. We also are talking about kinetics. So we'll be talking about the reaction velocity, and we're usually plotting this as a function of the substrate concentration, okay? The shape of this curve informs us about the appropriate model that will be used to mathematically quantify the enzyme kinetics. And we can get useful information from the plot, obviously. I'll talk about various characteristics about this momentarily. So just as a refresher from general chemistry, when you were introduced to reaction kinetics, we can talk about the first order reaction. And of course, you'll be talking about this in more detail in physical chemistry, where you have partials and so forth. But for our purposes, just a delta, the change in Product concentration over the change in time gives us the velocity for a first order reaction. This negative is the disappearance of the reactant, okay? P forms, that's why it's a positive number. And we can write this expression as such, where we have our rate constant times concentration of our own single reactant A. Second order reaction is similar. If we have two A's combining to form a P, don't forget that stoichiometric coefficient is the exponent. Or if it's A plus B going to P, you can write the expression as you see here. We can have, if we have A plus B going to P, and one of the reactants concentration is swamping out, is much higher than the other reactant, such that we have a limiting reagent of one of the reactants, then we can write the kinetics. It's considered to be a pseudo first order reaction, and we're basically writing the kinetics with respect to the concentration of A. Okay, that should make sense. And if it's independent of the reactant concentration, of course, that's a zero order reaction. So this should be a total review for you. So why in the heck would you care? As I said, this helps us understand the mechanism of a particular enzyme. We can determine if we have A plus B going to P, for example, we'll be able to tell, does it matter whether A binds to the enzyme active site first, or can B bind first for the reaction to proceed, or it doesn't matter, okay? So if you recall the citrate synthase induced fit example, the only when oxaloacetate as a substrate, the little teddy bear shaped molecule bound to the active site, only then was the second substrate, acetyl-CoA, able to bind to the binding site. So in that particular example, that sequential order was important. And this is the type of information that we can get from investigating the kinetics. Of course, the mechanism will be able to gain insight from the kinetics for that. If you're designing inhibitors, say you are a medicinal chemist and you're designing inhibitors, this is a way of assessing that. And of course, regulating the activity is always a key thing if that enzyme is capable of being regulated. Okay, so how do we do these experiments? In the lab, you have a test tube, okay? And enzymes work at a certain pH and certain buffer composition with certain cofactors and so forth present. So you have that all ready to go. You're in your cuvette, you pipette in a tiny amount of your precious enzyme that you've been purifying. Remember, the enzyme is not being consumed in this reaction, so you do not need very much of it. And then you very quickly pipette in your substrate, mix it up real fast, or have a stir bar, and you are assaying the activity. Typically, you're monitoring a change in absorbance at some wavelength as a function of time, okay? And so let's say you have a molecule that absorbs at a certain wavelength, okay? And that is the substrate. And so that absorbance will reduce as that substrate is being consumed and converted into product, okay? So you'll be looking at a decay. Alternately, you could have a substrate that is not a strong absorber at a particular wavelength, and the product is a strong absorber at that wavelength. And so you can monitor the increase of absorbance at that particular wavelength. And again, you're monitoring it as a function of time, kinetics, right? So, and then you'll be plotting the initial velocity and repeating at different substrate concentrations, okay? So as an example, here's a substrate that absorbs that particular wavelength. The product does not strongly absorb at that wavelength, so we're looking at a decrease in absorbance. There's a dead time because it takes time to mix the substrate and the enzyme together to get going. Okay, that's the dead time. We'll see that there are tricks in the next, maybe at the end of this chapter, in the next chapter, when we talk about stop flow, to go from, perhaps milliseconds to microseconds or sub-microsecond speed for mixing. Okay, then there is a decrease in this particular example. Okay, a linear portion of that curve before it starts to flatten out. Okay, so we are interested in the initial velocity. Okay, so if we look at another example here, the product is the species that is absorbing and who's at a particular wavelength that we're following as a function of time. Okay, so what we're plotting here is product as assessed by absorbance, for example, as a function of time. And at one substrate concentration, we get this plot, this lower one. Dump that out when the experiment's over, clean out our cuvette, set it up again, add a different concentration of the substrate, and we get this plot. Repeat and rinse, repeat and rinse, and repeat and rinse. Okay. Of course, as you're adding more substrate, your reaction is going faster, as you can see here. Okay. And what we are interested in is the initial velocity. So the initial slope, where this is somewhat linear. Okay. As you can see, we start to, as the concentration of the substrate increases, the initial velocity increases. It's this initial velocity, the change in product over the change in time, velocity, right? Just as you've learned in physics, that will be a data point when we plot our reaction velocity as a function of substrate concentration. Okay, so at substrate concentration 1, we have this initial velocity that we calculate from this product as a function of time plot. And this initial data point is that initial velocity for S1, S2, S3, S4, and so forth. Okay, so we, in our analysis of the kinetics, we're interested in the initial reaction velocity as a function of the substrate concentration. Okay, so when you are analyzing data, you start with a mechanism that you would like to model, right? And then you try to find the appropriate model that describes your data, okay? With every model, there are always constants and assumptions that go into that model. And if it doesn't fit your data, you need to go back to the drawing board and modify your model or identify another model that suits your data better, okay? So, and of course, you'll fit your data generally these days with nonlinear curve fitting, okay? But let's get down to the basics and work through the simplest model mechanism of all, okay? And I encourage you to work through this and carry out the algebra so it helps solidify these concepts in your mind. So in our simplest model, we have one reactant, substrate, okay, S, being transformed into one product, P, and there are no inhibitors to be found. Okay, so we do monitor the formation of product as a function of time, as I just described on a couple slides ago. So this initial substrate concentration 1, we have this initial velocity, and as we increase the concentrations of the substrate, you can see that the initial velocity increases. Again, we're interested in this initial slope, okay? It slows down, as you can see here, which is more clearly illustrated by S4 plot. It slows down because the substrate is eventually consumed as you start to reach equilibrium, okay? The process by which, as we start to approach equilibrium, this is referred to as the steady state. That is, macroscopically, if you are monitoring the concentration of substrate or product, you see no change in those respective concentrations, but the interconversion is still going on. Substrates being turned over into product, products being turned over into substrate. There's just no net change, okay? As a reminder, as we jump into this simple model of S going to P in the absence of any inhibitor whatsoever, we have our initial velocity that we plot, and that is each dot on this initial velocity as a function of substrate curve. Okay, so this is S1, S2, S3, S4, S5, S6, etc. It is critical to note that we are not, what makes this work is the only variable that is changing is the concentration of substrate that you're pipetting into that little cuvette, okay? We are not changing the concentration of our catalyst, the enzyme concentration. So let's work through what's happening mathematically with this simple model of S being transformed into P in the absence of inhibitors. And so this is the very famous Michaelis-Menten model that was developed in the early 1900s, 1911, 1914, something like that, and well before the advent of calculators and computers. But as you'll see, it is surprisingly robust and is well used today and describes many enzymes, not all enzymes, as of course. So let's work through this. And again, I encourage you to work through the algebra to, start to understand what the heck's going on. So, and this, back on page 27, when I was explaining some kinetics and so forth, and I was like, you know what, that slide 27 doesn't really, may or may not make sense to you, but it was kind of foreshadowing what was to come. We are now at that point. The foreshadowing is complete. And so the take home on page 27 was that our initial velocity is equal to our rate constant times the Michaelis complex, okay? So we're going to be using this moving forward, and you'll see where that comes into play. Okay, get back to the point. So remember, we described and defined our Michaelis complex is the enzyme bound to the substrate in an intermolecular, as a non-covalently, okay? And this is really the key to this Michaelis-Menten model. So we have our enzyme, our substrate, the Michaelis complex, and then if we continue moving forward, we regain our enzyme, and we now have product. And of course, we can write out this reaction with forward rates and respective backward rates. Okay, so if we are interested in the rate of the formation of the Michaelis complex, we can write that mathematically as the forward K1 rate constant times the concentration of enzyme times the concentration of substrate. This should be a total review of things that you did in general chemistry. Okay, the Michaelis complex is really key to this model. So let us write the expression that will describe the breakdown of the Michaelis complex. Okay, so of course we have to consider the concentration of the Michaelis complex, and this can go back to substrate with the kinetic rate constant of K minus 1, or it can move forward and be transformed into product with the rate constant of K2. Okay, that's why we have the sum of these rate constants. Now recall, we're looking at the initial velocities, okay, to help calculate. Here are our initial velocities of the plot that we'll be fitting, okay. If we're looking at initial velocities, then xNA, there's on the product concentration, because at the initial, when you start the reaction, the concentration of product is negligible, okay? So we don't need to consider P going back to the Michaelis complex ES with the rate constant of K minus 2, okay? So that is xNA, that is equal to 0. So that is one assumption for the Michaelis model. Just with that description, again, we have our enzyme substrate forming the Michaelis complex or breaking it back down into substrate. And because the initial concentration of product is 0, we can ignore the K minus 2. So now our chemical reaction only has the forward movement, the K2. Okay. The key, another assumption, in addition to the initial velocity, no concentration of P at the beginning, is the very critical steady state assumption. So what this is saying is that the concentration of our Michaelis complex remains the same, even though the concentrations of the substrate and the product are changing with time, okay? So what that means is the rate of Michaelis complex formation is equal to the rate of the breakdown of the Michaelis complex. There's only one way to form the substrate, or excuse me, there's only one way to form the Michaelis complex, but there are two possible directions for its breakdown, going back to substrate or moving forward to product, okay, as we described. So we can, at the steady state, we can set these two equal to one another, as you see here. Let's collect all the concentrations on one side and all the rate constants on the other side. Okay. To make things simple, let's call this collection of the rate constants the Michaelis constant, the Km, okay? So this is a collection in this particular model that of rate constants. This is not the equilibrium dissociation constant. It is not a KD, okay? We are not at equilibrium. We are only at the steady state. So the Michaelis constant is a parameter that is extremely useful, as we'll see in our discussions moving forward. Okie doke. So again, our reaction, we've defined Km. Now let's substitute it in and do a little bit of rearranging so we can define the concentration of our Michaelis complex as a function of enzyme concentration, substrate concentration, and Km, the Michaelis constant. We know how much enzyme we initially pipetted in our cuvette. That is the total enzyme. And the two possible species of this enzyme in your cuvette, okay, is either free enzyme or bound as a complex, okay? We know enzyme total. That is what we know. We don't know this, and this is hard to distinguish as well. So we do some rearrangement and substitution. So we substitute for E and solve for, again, the concentration of the Michaelis complex, okay? And through simple algebra, which I'll leave to you, we can define the concentration of our Michaelis complex as a function of the total enzyme. That is, you know exactly what you pipetted into that cuvette, and you know the concentration of the substrate that you pipetted into that cuvette, and a function of the Michaelis constant. Okay. The initial velocity is a definition of the formation of the product, right? Okay. And the only way we can get to product is going from the Michaelis complex with the kinetic rate constant of K2, okay? That will give us our initial velocity. That should make sense to you. So here we have our forward rate constant transforming ES to P, okay? Of course, this is a function of the concentration of the Michaelis complex. You know, how fast that reaction goes is dependent upon the rate constant and the concentration. Obviously, that makes sense. So let's do a substitute. And this is where we left off with the preceding slide here. Okay. So let's do a substitution, or let's think about this for a second. The fastest this reaction can go is going to be proportional to the total concentration of the enzyme. Okay, we define that as V max. Okay, that is cranking as fast as possible. So if we do some substitution, so what am I talking about? So here is, we define the concentration of ES as this expression. We substitute that in for here. And so we're defining our initial velocity as a function of K2. And this is what we substituted in from the preceding slide, algebraically. Okay. So at maximum velocity, all active sites are filled in that enzyme. So all of E is E total at saturation. And so V max is defined by K2 times E tot, which we substitute here for V max. And this, voila, biochemist, is the very famous Michaelis-Menten equation. Okay, our initial velocity is defined as a function of the V max, the maximal velocity, so only the substrate concentration and the Michaelis constant. Okay, so as you're doing kinetics, you'll be measuring velocities. You may or may not know the Michaelis constant. Perhaps that is the point of your experiment, but you do know how much dang substrate concentration, that you pipetted into that cuvette. So you know the concentration. I hope this makes sense. So this is our model for that is described by the Michaelis-Menten model and the Michaelis-Menten equation, okay? And so anytime you encounter an equation of some kind, you want to develop a sense of what is this describing at the extremes, okay? In this case, very, very high concentrations of substrate and very, very low concentrations of substrate, okay? And see if it makes sense when we plot out this curve. So if we plot the initial velocity as a function of substrate, we get this curve that is hyperbolic in shape, our initial velocity, and the substrate concentration, okay? And so velocity is always a per time, so concentration per time, or perhaps it's some moles per time, something like that, but it's a per time. Time is in the denominator since it's a velocity, and we're plotting our substrate concentration, which of course has units of concentration. So it's always important to make sure you have appropriate units for your experiment. Again, hyperbolic, what we see is as the concentration of substrate increases, we start to asymptotically approach Vmax. Where is this coming from? Okay, so at very high concentrations of substrate, much, much greater than the Michaelis constant. So effectively we have S only in the denominator because this is so much larger. This goes to 1. And at those very high concentrations of substrate, the initial velocity is equal to Vmax. Great. And that is what we see by this asymptotically approaching curve, approaching the Vmax, the maximum velocity. Now let's go to the other extreme when the concentration of substrate is much, much smaller than Km. Okay, so that becomes negligible. That term becomes negligible in the denominator. And so effectively the initial velocity is equal to Vmax over Km times the substrate concentration. So this is of course a linear relationship where this would be effectively the slope. So that is this point of the curve. Okay. Now, what happens when the substrate concentration is equal to the Michaelis constant? That is that the initial velocity is at 1/2 Vmax, okay? So, so if you know Vmax, and so that's what we see here at 1/2 Vmax, we drop that down, and that allows us to, that tells us where Km is. And you may say, hey, Sheets, Km was a collection of rate constants. That is true. That's how we mathematically defined it. Operationally, it is also useful because it tells us the substrate concentration at 1/2 Vmax. Okay, so that is extremely useful, and we'll be exploiting this idea moving forward. Okay, so again, the parameters, here's our Michaelis-Menten model. We plot it, okay? We can easily fit this with nonlinear curve fitting because we have fancy computers, and it allows us to determine Vmax. If we know Vmax, 1/2 of that initial velocity can inform us about the Km, which is the substrate concentration at 1/2 Vmax. That definition is only valid for enzymes that follow the Michaelis-Menten model in describing their kinetics. Okay, well, if you think back, this model was first described in the early 1900s, and of course they didn't have calculators and computers, and so, but it was easy to fit things with a ruler. Okay, so there are a few ways to transform the Michaelis-Menten model into a linear form. We will only focus on one way of doing that. That is the Lin-Weaver-Burke plot. There are others you should just be aware of as an FYI. So if we linearize the Michaelis-Menten model, we can get and transform it eventually. You do not need to do this transformation, so don't waste your time, but we can transform it into a linear form where y equals mx plus b. So y is 1 over the initial velocity. Our slope is this ratio of Michaelis constant over v max. X, of course, is 1 over substrate concentration, and the intercept is going to be 1 over v max. Okay, this gives us what we refer to as a double reciprocal plot. Okay, this is a very useful tool because, and this is the why people did it back in the days when before you could do nonlinear curve fitting, is it would tell you what Km was, as well as the initial velocity. And if you are assaying your enzyme in the presence and absence of various concentrations of a inhibitor and inhibitor, the slope will also, and the intercepts, as we'll see at the end of this chapter, will also inform you about the type of inhibition. So even though we are in the time of computers, this old school Linn-Weaver-Burke plot is in fact a useful tool. So it's really useful. You need to think units. So what we're plotting is y as a function of x, okay? Y is the inverse of the initial velocity. So it's 1 over the velocity, as you can see here. So this might be in units of micromolar, millimolar, micromole per minute, but it's always a per minute, right? Because it's velocity. And of course, x is the reciprocal of the substrate concentration. So 1 over whatever the concentration units are. It is important to note as you begin to approach the origin, the values are getting high because this is a double reciprocal plot. As you go further and further away from the origin, the values go down. So in the Linn-Weaver-Burke plot, the x-intercept is minus 1 over Km. Okay. The y-intercept is 1 over V max. The slope is the Michaelis constant over V max. And we'll come back to interpreting the Linn-Weaver-Burke plot when we start talking about various ways of inhibition. Okay. But first, let's start thinking about catalytic efficiency and what does Km actually mean. You know, the Michaelis constant was this collection of rate constants, mathematically defined as here. And we saw that Km is the substrate concentration in which the enzyme is at half maximal velocity, okay? And remember, the Michaelis constant is not an equilibrium dissociation constant. A useful kind of rule of thumb, which you may see moving forward, and particularly in metabolism, is that in vivo, inside a cell, the substrate concentration is typically on the same ballpark as Km. Okay, the substrate concentration where that enzyme is running at half maximum velocity. Okay, that allows the enzyme to kind of tweak and be proportional. So this is a concentration where you have enough enzymatic activity to take place. Okay. So Again, the Michaelis constant is not an equilibrium dissociation constant. It is not a KD, okay? But we can use assess the value of the Michaelis constant and think of it as a fake KD, a quasi KD. Okay, it is not a KD, it is not a dissociation constant. If and only if K1 is much, much greater than going the K2, the forward reaction going to product. Okay, under and only under those conditions, if we have a high Km, that indicates in an analogous way to what we learned about dissociation constants, KD, in the last chapter, a high Km indicates weak binding between the enzyme and the substrate. A lower Km indicates a stronger interaction, stronger binding between the enzyme and the substrate, okay? But again, the Michaelis constant is not an equilibrium dissociation constant, okay? Because we are at the steady state. But it's it gives us a sense of the affinity-ish, it is not an affinity, that substrate has for the enzyme. What the heck am I talking about? So here we have a variety of enzymes, okay, and different substrates. And so, and you can see it, they vary widely, okay. Now, if we look at the enzyme pyruvate carboxylase, there are 3 substrates, and you can see that ATP would have the highest affinity-ish. You cannot see me doing air quotes, but when I'm talking about affinity-ish, I'm doing air quotes, has a higher affinity than the bicarbonate anion, right? Okay. Vmax also reveals how fast an enzyme is turning over. What do we mean by that? So this is the Vmax over the total enzyme. And of course, this came about, Vmax equals K2 times E tote, from a few slides ago. In our discussion, we can define this K2, this transformation of the Michaelis complex into product, as Kcat. That's more commonly used. So Kcat is what biochemists refer to K2, okay? This is concentration per time. Enzyme, of course, is concentration. So we're left with per second or per time, okay? And so if we look at turnover numbers, we see our old friend carbonic anhydrase. The turnover number is, it is catalyzing 600,000 reactions per second. That is pretty amazing, okay? This is the turnover number, okay? The turnover number is whatever Kcat ends up being, okay? Because it's a per second, unitless per second. There can be some slowpokes as enzymes. Lysozyme, every 2 seconds, it catalyzes 1 reaction, so very slow. Next semester, when we talk about the world's crappiest enzyme, that's like 3 reactions per second in plants, in the fixation of carbon, and every 3rd reaction incorporates the wrong substrate. So that is a real slacker, as you'll learn. Okay. We can also, I think perhaps you might have homework that deals with this. We can also talk about the fraction of the active sites that are filled, analogous to what we saw when we were looking at the binding curve for myoglobin and hemoglobin, right? And so that is the rate, the initial rate at whatever that substrate concentration is over the Vmax. That is the fraction. So remember, at Vmax, all active sites are filled of that enzyme, okay? So this is this fraction that we can define as this, hunky-dory. Now, we also want to assess and get a sense of catalytic efficiency. Okay, and for that, we look at the ratio of kcat over km. Remember, kcat is K2. So kcat over km, if it is in the order of 10 to the 8th, 10 to the minus, 10 to the 9th, 10 to the 8th, 10 to the 9th, you know, so we're per second per molar. This is very close to a diffusion limited reaction. So what do I mean by that? As soon as that substrate hits that dang active site, boom, it's converted into product, okay? And you can recognize that it's a diffusion controlled reaction or diffusion limited reaction when kcat over km is on the order of 10 to the 8th to 10 to the 9th per molar per second. Boom, converts into product. Boom, converts into product. Boom, as soon as that substrate hits that dang active site, boom, it's turned over into product. And so, of course, there are many examples. And so if we just assess kcat over km, you can see, again, we're in the 10 to 8th, 10 to the 9th regime. These are diffusion controlled reactions. Okay, how does this happen? The approach to that crevice or cleft where the active site is located in the enzyme has intermolecular forces and so forth that kind of lure the substrate into the active site to help facilitate that interaction between the substrate and the enzyme that will lead to the transformation into product. So this is referred to as the Circe effect from the Greek mythology. And basically the enzyme is saying, come here, my pretty, come here, to lure that substrate into the active site. Okay. So the lower table just illustrates very nicely preferences for chymotrypsin. Okay, so let's think back to chymotrypsin. You learned in chapter 3 that this enzyme is useful and cleaves on the C-terminal side after bulky side chain residues, right? Like phenylalanine, tryptophan, and so forth. So let's look at the catalytic efficiency of glycine, the dinkiest guy, right? Remember, this is just hydrogen as a side chain. That has a catalytic efficiency kcat over km of 1.3 times 10 to the minus 1. So this is a pretty crap substrate. That is not a surprise, okay? Let's compare phenylalanine, okay? Which is recognized by chymotrypsin as preferential. We can see that its catalytic efficiency, while not diffusion controlled, is substantially higher. We're at 10 to the 5th per second per molar, okay? That makes sense. That is what this enzyme is made to proteolyze on the carboxyl side of phenylalanine. So this kcat over km tells you how effectively is that enzyme working on the substrate that you're asking about. Okay, so obviously this is not a diffusion controlled reaction, even in the presence of its natural substrate. Okay. Chymotrypsin is not one of those enzymes that is operating at super high efficiency, maximum efficiency, the diffusion limited reaction. And so how can you start to overcome these limitations is by channeling. So you have a multi-enzyme complex. So the product of one is the substrate for the subsequent reaction, as we have talked about a way of speeding things up. Or there's a channel inside the enzyme where there are two active sites and that intermediate product is diffusing within the complex. And you'll see some examples of that towards the end of next semester in metabolism. So there are ways of strategies of overcoming so to keep things clicking along. So again, Vmax, 1/2 Vmax is Km. That is the substrate concentration at 1/2 Vmax. Okay, so what we are limited to how reproducible your experimental hands are to get an accurate plot. That will probably be the rate limiter for you in biochemistry lab with your nemesis LDH. If you have contamination from your protein purification, your enzyme purification, you could have be affecting the activity of your enzyme. that may well be the case. If you in fact have purified LDH instead of purified water, and you haven't lost it, and it can age out with multiple freeze-thaw cycles and so forth. And even your substrate that you're using can be crap. So all these things, it's basically garbage in, garbage out. So you want to be as optimal and as clean, have as pure substrate and enzyme as possible in the absence of inhibitors, and have reproducibility in your technique of doing these kinetic assays and so forth. You will be experiencing the joy of this. I wish you well. Okay. You now can say, hey, Shitsi Poo, what is going on? If you go back to that citrate synthase example with the induced fit, there were 2 substrates. Okay, what is going on? The Michaelis-Menten model described 1 substrate going to 1 product in the absence of inhibitors. Are there ways of describing this and potential mechanisms? And I will say yes, indeed you do. Okay, so let's consider a reaction A plus B as substrates going to the products P plus Q. Okay, and so we will need to distinguish in a mechanism if you have such a reaction. Does the order of A plus B binding, is that important? Can it be random, or does it have to happen in a certain sequence? What about the release of the products? Can that be random, or does it happen in a certain sequence? Okay. And so 2 potential mechanisms that you need to be aware of are the sequential mechanism and the double displacement or ping pong mechanism. And we'll be looking at these in turn. So in sequential reaction, all substrates have to bind before any potential product is released. So this introduces us to Cleland notation, okay? This horizontal line represents our enzyme, okay? And for your frenemy, hopefully not a nemesis, of lactate dehydrogenase, LDH, we have pyruvate combining with NADH. Pyruvate is being reduced at this carbonyl oxygen to lactate. And if this is a redox reaction, so if something is being reduced, something else is being oxidized, NADH is being oxidized to NAD. The plus is always there. That has to be there, otherwise it is not correct. But we don't speak NAD plus, it's NAD, okay? So we could write this as an equilibrium, okay? It's a reversible reaction. So if we have our enzyme LDH, this horizontal line, NADH has to bind before pyruvate can bind. So this forms a ternary complex of the enzyme NADH and pyruvate. This ternary complex, there is simply driven through intermolecular forces. Okay, there is no covalent bond that is formed with the enzyme itself. Okay, pyruvate is transformed, reduced into lactate. NADH is oxidized into NAD. Okay, again, we're still in this complex of the 2 products, right, as a ternary complex. Then lactate pops off and NAD hops off, okay? So in this case, NADH comes first, pyruvate Pyruvate is the last on, first off, after it gets transformed into lactate, and then NAD comes off. Okay, this is what we refer to as an ordered sequential reaction. Okay, sometimes it doesn't matter. You just need one substrate to bind before the other substrate. Okay, this is an example of a random sequential enzyme. So again, this horizontal line is the enzyme. In this particular example is creatinine kinase. Okay, this is a way of generating ATP from phosphocreatinine and ADP, or we can phosphorylate creatinine using ATP. Okay, this is again reversible reaction. So we have our enzyme. And so one way ATP can bind before creatinine, we form this ternary complex of enzyme non-covalently bound to in complex with creatinine and ATP. Transformation happens to phosphocreatinine and ADP, and phosphocreatinine can hop off, ADP can hop off. Or we can have ATP creatinine bind to the enzyme. ADP can leave first, phosphocreatinine can leave second. Conversely, creatinine can bind first, then ATP, as you can see here. So that's what this bubble is showing us. And in this case, it's random with respect to the substrates, and it's random with respect to the products. Okay, so hopefully this makes sense. So, but before any product is released by the enzyme, all substrates must be bound to the enzyme to form this ternary complex. That is the very definition of a sequential reaction. That is in contrast to our double displacement or ping pong reaction. Okay, again, Cleland notation. Here is our enzyme. And so this is a very common enzyme that you'll encounter next semester, aspartate aminotransferase. We have our aspartate, you know that structure. You'll be transferring its amino group to this carbonyl, becoming a carbonyl. So aspartate is being transformed into oxaloacetate. Hey, that's a teddy bear molecule. It's an important molecule you'll become friends with next semester. After alpha ketoglutarate picks up that amino group, it becomes glutamate. You know that structure, right? What is the single letter abbreviation of aspartate? D. What is the single letter abbreviation of glutamate? E. Okay. Do not forget your amino acids. So again, enzyme, the aspartate aminotransferase is this horizontal line. We have aspartate bind to the active site of the enzyme to form this complex. It transfers its amino group and makes it covalently modifies the active site transiently. Okay. So the active site of the enzyme is covalently modified. That is the key of this double displacement or ping pong reactions. Once that amino group gets transferred to form this covalently modified enzyme, oxaloacetate, one of the products, is free to go. Okay. We're left with this covalently modified active site of the enzyme that is covalently bound in this particular example to the amino group that it got from aspartate. Okay, so in comes our second substrate, alpha ketoglutarate. That amino group gets transferred to the alpha ketoglutarate to become glutamate. Glutamate goes off as our second product, and we're left with our untouched enzyme again. So the difference between sequential mechanism is that we have this non-covalent ternary complex happening. Double displacement or ping pong is we have a covalent modification of the active site temporarily. Excuse me. We also talked about allostery. We were first introduced to allostery in our discussion of hemoglobin when we combined its oxygen binding as a function of partial pressure of oxygen to the hyperbolic, and we saw that sigmoidal shape, and we compared it to the hyperbolic binding curve of myoglobin. And we talked about the mechanism of that. And at that time, I kept saying that allostery is also important for enzyme kinetics. Voila, here we start to talk about that. And instead of that hyperbolic shape that we saw with the Michaelis-Menten model, okay, an allosteric enzyme, which does not follow Michaelis-Menten kinetics, which you can easily see by the sigmoidal shape, okay? The sigmoidal shape indicates cooperative binding. So this may be a multi-subunit enzyme with multiple active sites, analogous to what we saw with hemoglobin, okay? That was just a binding event. Enzymes catalyze reactions, okay? And you can have heterotropic, homotropic effectors that are either positive or negative in their cooperativity. And we'll talk more about this explicitly when we get into chapter 10. But just as we saw with hemoglobin, we can shift to the left, shift to the left, to the left, stabilizing the R state, the more relaxed, the more active state, to the left, to the left, to the left. Okay, that would be an example of a positive effector's effect. Or if we shift to the right, to the right, to the right, we're stabilizing the T state, the less active tense state. And this would be an example of inhibition. And so interpreting these allosteric plots is going to be key to understanding various modes of inhibition. And you need to be able to interpret these plots. And just a reminder that the sigmoidal shape is effectively a combination of the high activity relaxed R state and the lower activity tense T state. Remember, we can't distinguish those two curves. It's the sum of these two curves that leads to the sigmoidal shape. It's just like blue and yellow make green. You can't pull back the yellow and the blue from that, okay? It's a combo.